Hello, everyone, and thank you very much for the opportunity to present our work here to this community. I'm going to talk about inferring mantle viscosity through data assimilation of relative sea level observations in a glacial isostatic adjustment model. Let me first give a quick overview about our project. So our goal is to estimate mantle viscosities by as the title suggests, assimilation of relative sea level observations. We use the GIA model VILMA as a forward model and use also a particle filter. This research is done as a sandbox experiment where observations are taken from a reference run in an identical twin setup. We assimilate sea level rates of change because sea level observations only give relative data, and the rates of change are independent of the absolute values. We have two viscosity distribution parameterizations. The first is a simple three-layer model with two viscous mantle layers and a fixed elastic atmosphere. And the second is a 1D profile with 152 viscous layers and also a fixed elastic lithosphere. So what is glacial isostatic adjustment? That is the viscoelastic response of the Earth's surface to a changing mass load. If ice sheet forms at the surface, the lithosphere is bent, and viscous mantle material flows laterally away from the center of the subsidence. Global, in the opposite case, when the ice sheet melts, then the lithosphere shows an uplift and mantle material flows from the sides towards the center of the uplift region. The speed of the uplift depends on the ability of the mantle material to flow here from the sides towards the center. And by measuring the speed of the uplift, it is possible to draw conclusions on the viscosity of the mantle material. We use the numerical code VILMA for this purpose. It is a forward modeling code for the viscoelastic response of the Earth to the surface mass load. It needs an ice history as an input and an Earth structure, and uses a spectral finite element approach to compute the deformation at the surface. The sea level equation is then solved to obtain relative sea levels, which we use as observations in the study. The data assimilation method that we use is the particle filter. That's an ensemble-based method where each member develops individually. During the assimilation step, the particle's performance is estimated based on the difference between the forecast and given observations. And then each particle is assigned a weight. And depending on those weights, low weight particles are resampled to model states of higher weight particles. Thereafter, the viscosity values of particles are perturbed in order, on the one hand, to avoid filter degeneracy, and on the other hand, to adapt the viscosity parameters where needed. The output of such a filter is a weighted sum of the particle states, and that ensemble weighted mean then moves through the model state towards a more accurate estimation of mantle viscosity during the assimilation process. For the particle filter, we use the PDAF. So there are 4 steps in the particle filter: a forecast, then a weighting of the particles, a resampling, and a perturbation. For the forecast, we use the numerical code VILMA, and the weighting, resampling, and perturbation is performed on the basis of PDAF by Lars Nerger. The perturbation is in many cases the critical part. All the other steps are quite straightforward and work well, but the perturbation is tricky. We will see that later. That's the case when the model is more sophisticated. We use an identical twin setup. That means that the observations come from a reference run with the target viscosity values. It starts at some time in the past and runs until present day. And at certain points in time in the past, the ensemble is initialized from the model state of the reference run, and thereafter observations are taken at regular time intervals from the reference run and used as the relative sea levels of the reference run are used as observations for the assimilation. We take observations only at those locations where real observations from field measurement exist. Okay, this is shown here. Here's the distribution of real observations, and they were projected onto VILMA grid points. And in the global data set, there are 1,807 observation points. There are two subsets marked here in green and blue. The green one having only observations from North America and Greenland. The blue data set only observations from Fennoscandia and Northwest Europe. And later I use not only the global data set, but also the subsets as observations to show that the method also works with regional data sets. So in the first part, with the 3-layer models, we investigated the dependence on the observation uncertainty, the distribution of observations, and the observation period. Here we use the global data set and tested different uncertainties of the simulated observations. In the top row, there are 10 centimeters, 25 in the middle, and ½ meter in the bottom row. On the left side, you see the development of the RMS error for the relative sea levels. In gray are the ensemble members. Black is the global ice volume over time. And you see that with the onset of the assimilation, the RMS error drops quite significantly because poorly performing particles are already resampled to better performing particles, and it stays low until a time where there is a large drop in the ice volume and the model needs to adjust to the new drastically changed surface load. But after that, the errors drop again and stay low in all 3 cases. On the right-hand side, you see the development of the viscosity for the lower mantle in the left column and the upper mantle in the right column. The black line is the target viscosity of the reference model. The black line, yeah, and the red line is the ensemble mean. The gray lines are the ensemble members. And here you see that the ensemble mean in all cases quickly converges to the target viscosity. The spread of the ensemble is, as expected, larger when the observation uncertainties are larger, and it is smaller for the upper mantle because the deformation at the surface has a much greater impact in the upper mantle than it has in the lower mantle. And we will see that later in all the results that it's quite challenging to constrain the lower mantle viscosities because a small deformation at the surface has only little effect at the deep lower mantle, and therefore viscosity changes there cannot be well detected at the surface. Okay, in the next test, we used only observations from one of the regions that I showed you. Here, Laurentide in Greenland, so that's the North America region that was shown in green in the top row. We have in principle the same picture as when using a global data set. The uncertainties, that is the ensemble spread here, is a little bit larger, which is expected when only using fewer data. In case of the Fennoscandian region, it's even more difficult to constrain the lower mantle viscosities because the ice sheet was significantly smaller than the one in North America and has even smaller effect on the deeper mantle due to a smaller surface load. But even in this case, we have a convergence of the ensemble mean to the viscosity target values, but the uncertainty is higher than when using the whole observation data set. And in the third case, we used only data from the last 10,000 years. So here in the former two cases, we started with assimilation at 26 kilo years before present, that is shortly before the last glacial maximum. And here we started the assimilation 10,000 years ago, so right after the deglaciation, where there's only an elastic rebound and no more significant melting of the ice sheets. And here the ensemble, the arrow drops quickly, stays very low, and the ensemble mean converges quickly to the target value in both cases here for the 25 or 50 centimeter observation uncertainty case. In the next part, we investigated a 1D profile of viscosity distribution, not only two regions as in the first part. And here we had a closer look, especially at perturbation strategies of the profile. The first strategy was to just scale the profile with a common factor, and in the second part we try to also change the shape of the profile by parameterizing with cubic splines and changing the spline knots, and the third part is a combination of the first two strategies. The green line here is the target viscosity profile that we try to fit. The black dots are the spline knots for the cubic hermite splines. There are 20 knots. We did this to ensure some smoothness of the profile, because if you change every of the 152 layers individually, this becomes very, very rough. There are a lot of undulations, and it's very difficult to obtain a smooth profile. We will see that it's even a challenge when parameterizing it with splines. The values for the spline, for the mantle viscosities, are then obtained by spline interpolation. Here's the first case where the profiles of the ensemble are only scaled in this log-lin plot, where the viscosity is on the x-axis, the radius of the Earth is on the y-axis. So here's the surface, here's the core mantle boundary. This corresponds to a horizontal shift. And you see that here this is the initial ensemble, that after some time steps, this ensemble moves towards the black profile, and after some time the red mean matches the target viscosities. When we use spline interpolation and adjust the individual spline knots, you see that we start here with an ensemble that's slightly off the target ensemble, and the upper mantle part here is matched quite quickly, while the lower mantle takes some more time at the upper part of the lower mantle and even is not matched very well for the deeper part due to the flow and a small deformation here. But still there is a match in this region here. If we combine these two approaches, we have the following picture here. I started with a profile that has a totally different shape than the target profile and has an offset. And in the first part of the assimilation, it's only shifted until there's no further improvement in the RMS error due to shifting. Then the spline parameterization and adjustment of the spline knots sets on, and you can see that from this shape, the profile can converge to the target profile. This is also quicker for the top parts here of the lower upper mantle. A little bit more difficult with more undulations here for the lower part because this is not well constrained. So the next step would then be to improve the profile smoothness by maybe adding some smoothing algorithm after the perturbation, or also important are more steps towards more realistic temporal observation distributions, and to account for temporal observation uncertainties, which is quite tricky when we use rates of change, because then the ratio of two Gaussian distribution is a distribution with no statistical moments. So this is quite tricky to handle. And the next big task is to couple the ice model and the viscosity model to have a joint assimilation for both models. Finally, I want to acknowledge the Helmholtz Association for funding this project through the Advanced Earth System and Modeling Capacity program. And I'm open for questions. Thank you.
Thank you very much for your talk. So we already have a question by Lars. And so I'm just reading it out to you. On slides 14 and 15, the initial ensemble is biased with too high viscosity. So did you attempt to avoid such a bias with the initial ensemble? And there's also the comment by Lars that the particle filter is not particularly good if the observation is not within the range of those ensemble.
Let me see if I can read that question. Places too high viscosity. No, actually, that was done on purpose because the viscosity in the mantle is or estimates of the viscosity vary depending on the research group by several magnitudes. So the task or the goal was to find an algorithm that can find the correct distribution of the viscosity, even if the initial guess is far off the true value. So this was the purpose, and I think this is even here on 14. This is even still quite close to the target value. So we would like to start with an initial example that is even farther off the true values, which we did here. here it's even farther away, at least in this part. It's here several, at least 2 magnitudes, maybe 1.5 or a little less than 1 in this part. But filters even here able to converge. The ensemble mean moves here towards lower viscosities, and then from here we can start to adjust the profile shape.
I think the argument was that you might just have a particle collapse if you're too far away from the, because all your weights become essentially 0, and then your effective sample size is really small, and that was maybe the argument.
Yeah, that's right. That's why we the perturbation then is important, because we if the effective sample size becomes very small and we use a clever perturbation, then we have or remaining variance in the ensemble with which we can then further work on.
Interesting. And I don't know if Lars has not replied. Yeah, he's happy with that answer. One question I had was regarding, I mean, you essentially, you don't have a stochastic model, you use the perturbation to somehow also, increase the spread of the ensemble to somehow reflect more the uncertainty in the model. And you talked a lot about the, but do you have, is there any plan to maybe also look further into the actual, because you now do a lot of work in the direction of perturbing, to actually figure out what the uncertainty in the model is, and to somehow use a stochastic model rather than going by the perturbations?
That's at the moment not on our immediate agenda. No. Maybe something that's worth thinking about, but
or to somehow get a better grasp on this model error, to somehow but yeah, thank you so much. I don't know, thank you for giving this talk, and I don't know if there are any if I'm supposed to say some closing words, or if Nora wants to.